Okay, so this is a talk I originally gave at tomorrow's Mathematician Today 2013 on the 16th. It's called Geometric Approaches to Solving Diophantine Equations. I thought I'd record it here for self-evaluation, and if someone else gets something out of it, then that's great. The conference was great fun, and I highly recommend any undergraduate to attend or something similar if they can find something. But let's get into it. Okay, so first of all, what are Diophantine equations? They're named after Diophantus of Alexandria, who lived approximately 250 AD, and he studied equations like the ones we're going to talk about today, and they're generally taken to be sort of polynomial type equations where they have integer coefficients. It's probably best if I show you a few examples, and then you'll get an idea of the sort of thing we're talking about. So Pythagorean triples, an example of a Diophantine equation, quite a well-known one. X squared plus y squared is z squared. We look for solutions like 3, 4, 5, which are integers which satisfy this equation. Pell's equation is another quite well-known one, where you have x squared minus ny squared is 1. And this has solutions for most n, but when n is square, you don't tend to get solutions. Whereas the Pythagorean triples, there's a good deal of solutions for those. The next one is x cubed plus 48 equals y to the fourth. This one actually has no solutions, so you can see it's quite hard to tell just from looking at them whether they will be, soluble or not. So the last one is 9 to the x minus 8 to the y equals 1. So this is quite different again, but normally considered to be a Diophantine equation still. And this only has the one obvious solution, which is x is 1, y is 1, and no others. So what sort of questions might we want to ask about a Diophantine equation? The sort of things we would ask are there any solutions, first of all? And we'd ask this over different sets of numbers. So we'd say, are there any integer solutions maybe? Or maybe are there any rational ones, depending on the form of the equation. Then we might want to ask, how many are there? If there are some, are there finitely many, infinite, countably, uncountably infinitely many? Can we somehow classify the number of solutions? Okay, and then can we actually classify the solutions themselves? Do they all lie in, say, an arithmetic progression? Are they all prime? Are they all squares? How can we talk about every solution? And possibly, how can we compute them? So if we've got a finite number, can we compute them efficiently? An infinite number, obviously we can't compute them all, but how can we compute efficiently the ones below a certain number, for example? So in this talk we're going to talk about two general ideas. The first is called geometry of numbers, and it's quite a nice way of showing that solutions exist to equations. And the second idea is about rational points on surfaces, and we'll see a bit more about what these are later, but let's just give you a quick overview. So geometry of numbers, first of all, Hermann Minkowski, who's the charming chap on the left there, in 1910 published his paper or book called Geometrie des Zahlen, which literally translates to Geometry of Numbers. And in this he introduced a number of theorems, results, all sorts of new things. It's quite a long document, and he sparked this whole field. It was really just developed from this paper, and it's still an active area of research today, and we'll see in a second some of the uses of it. So we're just going to go for an example here. Is we want to find integers x and y such that x squared plus y squared equals p, where p is prime. So if I give you a prime p, can you find me x squared, x and y such that x squared plus y squared is equal to p? So we might try a few things out, a few primes, and we'll notice that 5 is 2 squared plus 1 squared, 13 is 3 squared plus 2 squared, 17 is 4 squared plus 1 squared, so they all work. Maybe we try 7, and a few others, 7, 11, 19, well, they all don't work. So maybe we try a few more, and we puzzle over this for a minute, and we might eventually see a bit of a pattern emerging, that the primes which do work all have remainder 1 when divisible by 4, and the primes which don't work all have remainder 3 when divisible by 4. There are no primes with remainder 0, because then it would be divisible by 4, and there's only one prime with remainder 2, so we don't worry about that. So maybe this is only true when P is congruent to 1 mod 4, to use the congruence notation. And this is actually a theorem that Fermat first came up with, and it's sometimes called Fermat's Christmas theorem because he wrote a letter to Mersenne dated Christmas Day, which gave the first claim of this result. And it has a number of ways of proving it. Indeed, Fermat did prove it long before Minkowski came along. But it's got quite a nice proof, I think you'll find, when we use the geometry of numbers ideas. So he just says, what we've sort of conjectured here is, an odd prime P can be written as P equals x squared plus y squared only when P is congruent to 1 mod 4. So how do you go about proving this? Well, x and y are very convenient names, so we might try plotting these points on the plane, and we can see that, say when P is 5 in this example here, we have a circle of radius root P, and we're looking for integer points that lie on the circle. So the red dots here are the points 2, 1, 1, 2, minus 1, 2, minus 2, 1, etc. And we can see that these are all solutions to our equation. Generally, we'd probably only recount this as sort of maybe one solution because, well, obviously we can take negatives because we're squaring, so it doesn't make a difference, and we can swap x and y around. But these are really the sort of the 8 solutions for P equals 5. And how can we try and analyse this? Well, maybe we could try and say, instead of x squared plus y squared equals P, we look for points where x squared plus y squared is a multiple of P. So maybe when x squared plus y squared equals 10 or 15 or 225 in this case. So why don't we try plotting those as well, and we get quite a lot more solutions here. And we can see they've got quite nice regular patterns to them, obviously from the symmetry of being able to take negatives of the x and y's again. In some ways now we have rather too many solutions. So what I'm going to do now is maybe a little bit odd, but I'm going to ignore roughly half of them, and this corresponds to making a choice on the congruence level, but what we can see is that we actually have one set of solutions that we've just kind of rotated around a bit to form the other set. So if we remove these, I won't get into details, but we end up with this set of solutions. So these are all sets of solutions, and it doesn't matter that I've forgotten about the other ones because I'm only trying to prove that a solution exists here. So if I can prove that a solution exists from this set, then I can prove that it must exist. Well, clearly one must exist. So I haven't lost anything by ignoring these other points. But the reason we've done this is so we can see this nice regular grid-like pattern, and this is what's called a lattice in R2 in this case. So we've got these nice grid-like structures, and we can see that really what we want to know is if all these points are where x squared plus y squared is a multiple of p, we want to know, is there one sufficiently close to the centre that has to be equal to p? Okay, so what we can actually do is we can take a circular radius root 2p, and we can see that if any of the points lie inside this circle, not on but inside, then we know A, they have to be less than 2p, and B, they have to be some multiple of p, the sum of the squares. So we can see that they must in fact be our solutions. We're going to ignore 0 here. Obviously 0 is another point, but we don't really care about 0 because it doesn't satisfy our equations. So really we want to prove that there's one of these lattice points that's not 0, that's inside this bigger circle of radius root 2p. So Minkowski gives us a theorem. So first of all, we're just going to introduce a little bit of notation here. We say a set B in Rn is symmetric or centrally symmetric if when we've got one point in our set, its negative is in our set. So, okay, this makes sense to what we'd normally consider to be a symmetrical object. So obviously our circle was, ellipses are, squares are, little diamonds are, So this hopefully won't limit us too much. And we're also going to say a set B in Rn is convex if x and y are in the set. Then every point on the line joining them is also in the set. So we can write this in symbols, and we've got it there. But really what we're saying is that we take any 2 points in the set, we join them up, and every point on that line is going to be within the set again. So this kind of makes sense again with what we'd normally consider to be something that's convex. So Minkowski then gives us a theorem in his paper, and there are a number of forms, but this is the one we're going to use today. So we say if B is a convex symmetric body, or a set, for us it makes no difference, and lambda is a lattice in Rn, then B contains a non-zero point of the lattice if the volume of B is strictly greater than 2 to the power of the dimension of the space. So in our case we had the plane, so it was r squared, so it would be 2 to the 2, times I. So we've got greater than 2 to the d times I. And I here is the area of a single cell of our lattice lambda. So back in our example, it was our squares, so it would be the area of one of those squares that when you take them and put them alongside each other form the lattice, or the corners form the lattice. We can find this area using determinants, or the order of our lattice as a subgroup of z to the n, if you're more algebraically inclined. But intuitively it's just the area of this cell that gives us our lattice. So we should try applying it now. So our circle in R squared is symmetric and convex, which is great. I'm not going to show that. And the area of our lattice cell is P. Like I said, there's a couple of ways of seeing this. Probably have to take it on trust, but it's quite easy to see that in our case the area of our cell is going to be P. And now the area of our circle, which remember had radius root 2p, our larger circle, so the area of our circle is going to be pi r squared, so pi times 2p. Okay, so let's see what Minkowski tells us. So Minkowski tells us that the volume of the body, which is pi 2p, is in fact greater than 2 to the d times I, which in our case is 2 to the 2 times p, which is 4p. So this equation actually just reduces to pi is bigger than 2. And so we do have a point which satisfies x squared plus y squared is a multiple of p, a non-zero multiple, and also it's inside our bigger circle, so we know that it's less than 2p. So we can take these two conditions together and conclude that x squared plus y squared does in fact equal p, and we know this point must exist by Minkowski's, and we're done. We've proved Fermat's Christmas theorem. So it's quite surprising to me, at least, that the fact that pi is, 3.1415 rather than 1.918 has an influence on this Diophantine equation being soluble or not. Obviously, like I said, there are other ways of proving it, and we could have taken a different body. So it's maybe not quite a property of pi, but it's interesting that the geometry of the space has a bearing on whether our equation is soluble. So we're going to move on to something a bit different now, and I'm going to talk about rational points on surfaces. So Euler looked at the equation a to the 4 plus b to the 4 equals c to the 4 plus d to the 4, where a, b, c, and d are in rationals, so they're fractions. You can see that this is actually kind of equivalent to asking the question about the integers. So if we find rational solutions, we can multiply through by all the denominators, say, and generate an integer solution. So even if we only want to find integer solutions, we could just find rational ones and then perform this process to find integer ones from that. This in fact defines a surface, or a hypersurface, in R4, so obviously I can't give you a pretty picture of this one. And Euler found a parameterization of the solutions. This one's from Hardy and Wright's Introduction to Theory of Numbers. So it gives us four functions, which take in two variables, s and t. We can see that they're complicated but manageable. So we can put in a rational s and a rational t, and we'll get a solution to our equation out. And Euler was the first to find solutions to this using a different, but once again a parameterization. He was wrong at first, but corrected himself, so it's all fine. And we can actually, look at all the solutions as they are given to us by this equation, and we can ask how many there are. There's one problem though, in that not all our solutions are of this form. There are other points, other rational points on this surface that aren't generated by this parameterization. So that's a bit of a sticker, but we're going to move on. So say if we had a different problem, in which, for example, if we take the same equation but with cubes, there is a parameterization which does generate all the solutions. So these techniques are of use. If we're going to ask how many solutions there are, that's not really a very well-defined question. Obviously, there are going to be infinitely many if we have such a parameterization. So if we want to find a good way of counting them, we're going to need a better way of saying, how big is a rational number. For example, if I say how many rational numbers are there less than 1, there's still an infinite number. How many less than a half? Still an infinite number. How many whose absolute value is less than a half? Still an infinite number. So we don't really have a good way of counting our rational numbers. Counting the number, which we would like if we're going to kind of estimate and compare how many solutions one has to another. Because we can talk about how many there are less than a given bound, but we can't do it with our normal absolute value, our normal way of measuring the size of a rational number. So we want a different way, and this leads to the notion of what's called a height. So what we're going to do is we're going to take our rational number in reduced form. So a over b, where a, b are integers, and they're coprime. So we've reduced our fraction down as much as we can. And one way of counting kind of working out how big this is to look at, say, the length of a and b, how many digits they contain in their base 10 representations there. And we can use this actually to define a better bound. So saying how many digits corresponds to taking a logarithm. So we're going to say that the height of x is the max of the logarithm of a and the logarithm of b. And we're taking absolute values here just to make sure that the logarithms play nice. And this height function is actually a better function. So we're sort of measuring the arithmetical complexity of this rational. So under this new height, although in the normal way of measuring it, 1 over 10 is very, 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 very close to 1000 over 10,001. In this new height, this new way of measuring the heights are very, very different. So what we can see though is that there are only finitely many points with height less than a given value. If we limit the number of digits the numerator and denominator can have, we're gonna only have a certain number of choices for each, and so we're only going to have a finite number of rationals with bounded height. So if we now want to count points with bounded height, we can do this in kind of the obvious way and define this function n. So we say nxb, so x is a set and b is a bound, just a real number or whatever. So we define nxb to be the number of x's and x, so the number of rationals whose height is less than the bound. So this is quite an intuitive way of counting the points of bounded height. It's really the sensible way of counting them. And what we can do is we can analyse the growth of this function as b grows. Now, there are very, very deep conjectures by Manin and others about the growth of nxb asymptotically, and they state that it's governed by the geometric properties of the surface for a good number of problems. And this is really interesting because where we started with, what we thought was a relatively, maybe a number theoretic problem, we're just looking for rational solutions to this polynomial equation, we've actually found that the number of solutions is conjectured, and there's a lot of evidence to support this, and it's been proved in a few cases, that the number of these solutions grows based on some geometric invariant. The morals of this talk are that geometry can help us show solutions exist to Diophantine equations, and geometric properties can govern the density of the solutions. So these, two small, tiny parts of the intersection of geometry and Diophantine equations give a bit of a flavour of the sort of things that you can do with geometric tools. And there is a hell of a lot more going on here. There's so many interesting things that happen in this area, and there's a whole area of arithmetic geometry, or Diophantine geometry sometimes called, a massive research area that looks at the connections between geometry and Diophantine equations, number theory, that sort of thing. Just a couple of references. Thanks very much for listening.